Hi everyone. I made this video to show what I am looking for when I look at a student's lab notebook in organic chemistry, and especially if the lab they are doing is an organic reaction. So there are things that need to be written in the notebook before coming to lab. That's called the Prelab entry. And in particular, for a reactions lab, I want my students to show a stoichiometry table. Why do I want my students to write a pre-lab entry? It helps them prepare for lab, so they use their time wisely. As they're writing their pre-lab entry in their notebook, they may be able to predict possible obstacles. For instance, when will the balances be very occupied? Or when can they possibly use the hood for instance, a reaction or a step that produces a lot of fumes. Third, maybe as you write through your pre-lab entry, you can start game planning. What do you plan to do during the lab, and what would your partner do during the lab? Can you delegate the different tasks between you and your partner? Also, it will help you anticipate what to look out for. When do you really need to pay attention during action? Or when do you need to really observe what's happening when you do the workup? A workup is another way to say isolation of the product, or purification. More isolation of the product. Purification, there are other techniques that you'll see as you go through organic chemistry. But after the reaction, you do a workup, and then you do a purification, and then typically characterization and analysis. So the first thing at the very tippy top, you want the page number, the date, and the title of the lab. Okay, so I understand that many of you who are watching this video have not read the procedure or do not know what's happening in this particular lab. Well, we're running a reaction. So the next thing, typically, the pre-lab entry is a graphical abstract. And the graphical abstract I have here, normally you want to put the reaction, the theoretical yield, and I'll show you that under the product, and also the glass setup. Okay, even if it's as simple as what we have here, which is just a little test tube reaction. So the reaction that I'm showing is the synthesis of eugenol benzoate, which is right there. Okay, if you run out of space on the on the right, go ahead and just put it underneath. And what's important for me is we anticipate what the theoretical yield is, how much we expect. Do we expect 40 grams, or do we expect 10 milligrams? The other thing is, these are the two starting materials, two compounds. I don't want to write, this is eugenol, and this is benzoyl chloride. I don't want to keep writing that name over and over again. So in literature, they give it a number usually. And they can refer to that compound by the number. Now in literature, in an article, that number is usually bold, but we don't have like a bold function when you're writing. You could draw it bold, but it's kind of hard to tell whether a person wants it bold or not bold. So I use a little squiggly line underneath to indicate that this isn't indicating a specific compound. Okie dokie. The theoretical yield. I want the theoretical yield underneath the product because I want my students to anticipate how much they should be getting. So I'm going to put this in a box. And the issue is, how do we calculate the theoretical yield? And it's going to be, in this case, in grams. Okay, so you are, for most organic reactions, going to determine the limiting reactant. Yes, a little bit of Gen Chem is coming through, and let me show you those calculations. Now the thing is, you haven't read the procedure, or you don't know the procedure well enough to know the amounts. So I'm going to point that out to you, because we're going to use in the lab 0.5 grams of eugenol and 12 drops of benzyl chloride. But how do we convert that in numbers that we could use to figure out the limiting reactant? Okay. So this is on the right side of the notebook, the odd numbered pages, and my calculations typically are on the left side, and so this is page 34. Now, I am a little bit particular. So on the left side of the notebook, usually I want my students to put the pre-lab lecture notes and any calculations. Actually, I tell my students that I am not looking at the left side of the notebook unless they want me to double check something. I only typically look on the right side of the notebook. So what is on the right side? Well, yeah, we started the pre-lab entry on the right side, the odd numbered pages. Observations, definitely I want to see. Data, I want to see. So anything that the instructor wants to see, I would put on the right side of the notebook. Any other supplemental notes or calculations that are not necessarily important for the instructor to see is on the left side. So, is this thing trying to autofocus? Oh, there we go. Okie dokie. Determine the limiting reactant and theoretical yield. The idea is we have two main compounds in the starting material, and we pretend what if each one is a limiting reactant. So eugenol. If eugenol is the limiting reactant, then we're going to calculate how much product we should get. So I have 5 grams of eugenol, 0.5 grams of eugenol, times, or really it's divided by the molar mass, but it's 1 mole over the molar mass. Okay. Because what am I trying to do? I'm trying to cancel out units. And this is called the mole bridge, because I have now moles of eugenol. If I stop there, I really want moles of the product eugenol benzoate. But it's a 1-to-1 ratio. And how do you know it's a 1-to-1 ratio? You have to gain an intuition about this, because you know this product, most likely this left half of the molecule is coming from compound 1, and this right half of the molecule is coming from compound 2. See how there are 2 rings here? So it's a 1-to-1-to-1 ratio. Now, so I use a mole bridge, and at this point I have moles of eugenol benzoate. I could literally cancel out eugenol, moles, eugenol. That's the molar mass of the eugenol benzoate. And so I get rid of, what do I get rid of? Moles and moles. And I have now grams of eugenol benzoate. So that is the amount that I get if eugenol is a limiting reactant. Okay. Again, you may want to pause and try to do these calculations on your own, knowing that we are going to use 0.5 grams of eugenol. Now, if benzyl chloride is a limiting reactant, in the procedure I said 12 drops. And I also put in procedure conversion, because 1 drop is equivalent to 0.050 milliliters. Well, if we want moles and be able to use a mole bridge, I got to get to grams, and then I got to use the molar mass to get to moles. So let me show you how those units cancel out. Drops, drops. Milliliter, milliliter. Grams, grams. So what am I doing? I'm ultimately, in this first line, getting moles of benzyl chloride. But I really want moles of the product. So there's your mole bridge, right there. And then that means I could get rid of benzyl chloride, and this mole, right there. Then I multiply it by the molar amount of the product. So mole, mole. So I'm left with, again, grams of eugenol benzoate, and there's my theoretical amount if I use up all of the benzyl chloride. So the thing is, before I even get this much amount of eugenol benzoate, the eugenol is going to run out. So eugenol is limiting. The limiting reactant is the one that runs out first. since usual makes less product, we're going to run out of usual when we get this much product. We won't have enough usual to react the excess benzyl chloride to get this much product. So you pick the smaller number. Usual will run out first before benzyl chloride does. Therefore, usual is the limiting reactant. Oh, you don't see that. There we go. And theoretical yield is 0.817 grams because I'm picking up this number right here. Okay. So you'll do those calculations for the amounts that you plan to use and figure out the limiting reactant and then the theoretical yield, which is 0.817 grams. I will deduct points if I don't see the theoretical yield. I want you to have a good idea how much to expect. Okay, so we expect less than a grams. Now, the setup, because I want the glass setup also, it's just a test tube reaction. We do all the reaction in the tube, and I want to at least show a little bit the order of addition. So in the test tube, you'll have one first, and this is just coming from the procedure. And then we did use 12 drops of benzyl chloride, and that's in a dropper bottle, so that's why I have this drawn out like that. First the KOH, then the benzyl chloride. It's an interesting reaction, but I'm not going to have time to go over the mechanism. Okay. The acid-base reaction between that OH and the KOH, right, is something you should know, but the rest of it is organic chemistry too. But we're not worried about the actual mechanism. We're worried about how do we set up the lab notebook properly. Okay. So after the graphical abstract, which is what this is called, the reaction and the glass setup, we have a purpose. And the purpose is to synthesize eugenol benzoate, a solid derivative of eugenol. We want to do this because we want to get a melting point. And this is an oil. This was I did actually in the previous lab, and we want to verify that this is really eugenol by making eugenol benzoate and getting them melting. Now, next week we'll do a recrystallization followed by TLC and melting point analysis. The purpose is, for me, very informative. The purpose, you want to be direct. What are you literally doing? You're synthesizing something. You're getting the melting point of something. You are purifying a product, something. You want to be, what are you going into lab to do? You also want to give details. So you want to be direct and brief. You want to give details such as what chemicals are you using, what technique maybe are you using, and why. So here we're making eugenol benzoate in order to get a melting point of the solid derivative. Again, because eugenol is an oil, this is a liquid actually, so this is your solid. Okay, so that's the purpose. Oh, the other thing is, see, I made a mistake here. I started to write derivatize. I meant to write a solid derivative. As you know, in your lab notebook, you never use pencil, but here I'm also demonstrating that never erase mistakes, never erase typos. Just strike through once or twice, and then make your correction. Okay. Lab notebooks, it's not a good practice to have erasing in lab notebooks or have something totally blacked out. You're sharing your lab notebook with future scientists that are going to be in the lab. Okay, you don't want to hide anything, even if it's an honest mistake like a typo. You don't want to hide it. Okay, you want everything to be visible for the next person, just in case they want to reproduce your experiment. Okay. Source. This is from the lab handout from our course. Synthesis of eugenol benzoate was the title of the lab handout, and it was emailed, and it's also on Canvas, our course website. Okay, so far so good? Alright, next. Chemical characterization. For the chemicals characterization, list all the chemicals you'll be using, and you're going to fill this out when you see the chemicals. So this will be blank at the beginning of lab. You'll have it set up, but then you're going to put the characterization. Okay, I'll get to this in just a bit. So you want to tell your instructor whether you're working with a solid, liquid, or gas. What is the color of that substance, and what is the clarity? Is it transparent? Is it partly cloudy? The reason why I want to do that is for practical reasons. If we get a low % yield at the end, I actually want to know, well, is it because we might have a degraded starting material? Okay, so for instance, what number 1 should be clear brown oil. But what if it was, black? I still want to know if it works, the reaction works. And if it does work, beautiful. I know that not to be worried about, a black colored eugenol. But what if the % yield was low? Then I could go back and say, well, maybe it wasn't that great that eugenol was that color. Okay, but we don't know. We don't know if it will work or not. We just want to make sure we get all the characterization so we could, at the end, if there was a problem, we try to identify, well, what could be the problem area. And it could be actually the starter material, degraded or impure. It's just good practice to write what it looks like at the beginning of the lab. Now, with that being said, clear is not a color. So if you have a liquid, instead of brown oil, right? Well, that brown oil can also be clear. So if you have something that looks like water and you just say it's clear, I will wonder, well, clear means transparent, but it doesn't mean what color it is. If you have something like water, you should describe it as clear and colorless. Okay? You have a clarity and you have a color. All right. Next are the hazards. The same chemicals that you have in your chemicals characterization, you want to look up the hazards. And you want to look up, you could use Google, okay, and you want to pick up what possible dangers these chemicals have. For instance, 1, eugenol as an irritant to skin and eyes. So that's with a lot of chemicals. You have extended exposure. Number 2 is a little more serious because in the procedure I said it dispenses in the hood, the fume hood. So you want to avoid inhalation because it is a possible carcinogen if you have prolonged exposure. KOH is a very strong base, and you know that from general chemistry. Wear gloves, it could cause burns. And then ethyl acetate, if you have long exposure, it could cause dizziness if you inhale the fumes for a long time. This is the second page of the Prelab. So this is on the right side of the notebook, and again, put your page number. This was page 35 at the beginning, 37. So the things that you want your instructors to see should be on the odd number pages. Again, your Prelab lecture notes and your calculations can go on the even number pages on the left side of the notebook. Okay. Next, and most importantly, I think, is the stoichiometry table. And you're going to fill this all out even though you haven't measured or weighed out any chemicals before lab. So you're going to use the planned amounts. And the other thing is, for the stoichiometry table, just list the chemicals used to determine the limiting reactant and the theoretical yield and the product. So nothing solvent, nothing about these helper molecules like base, or this is a solvent, acetate. Actually, this is part of the extraction procedure. So I only have 1, 2, and product. Give the molecular weight, and only if it's important and useful, give the density. And it was important for number 2 because that was in the dropper bottle. We needed to convert the milliliters into grams. Okay. Then give the amount that you're using in grams, or in this case drops. What's in this box? That's our theoretical yield. That is the same number that we have in this box right here. And I put a little note here that it's expected. So this is not actually what we got, but this is what we calculated. So here's where some students have difficulty. Well, first of all, I ran out of space, so I had to continue the table a couple lines down. I want the moles. The moles of the two starting material. The moles of the things that we needed to use to figure out the limiting reactant. And then the equivalence. And this is what people have sometimes trouble with. The equivalence is a way to show the reader real quickly what chemical is in excess and by how much. Like when you're, when you're making bread, right? You have maybe 2 parts flour, 1 part oil, or a half part eggs. Now you could scale up, right? Those parts could be anything. It could be liters, it could be cups, but it gives you a very easy way to know how much excess the excess reactant is. So the trick is, whatever is the limiting reactant, make it 1 equivalent. Make it 1 equivalent, and then just do a ratio, right, with the moles. So what am I going to do? I'm going to solve for x and put it right here. To do that, you cross multiply. 0.00516 times 1 equals this times x, so we divide by this number, divided by 0.00305. Now, before I show you the answer, does it make sense? Well, this is larger in moles, and the reaction is a 1-to-1 ratio. So we would expect the equivalence to be larger than 1, because the amount of moles is larger. Now, that's not always going to be the case, because the stoichiometry, your ratio could be a 1-to-2, 1-to-2, or 1-to-3. You have to do this on a case-by-case basis, but the trick is the equivalence is literally the mole ratio. So I'm going to press enter. 0.69. Good. No, not 0. 1.69. Ooh. But that's good, because I estimated that this number should be bigger. So it wouldn't have made sense if I wrote 0.69. Okay, so that's the equivalence. So it's about 50% more than it needs to be. In organic synthesis, it is useful sometimes to have 1 reagent or 1 reactant in excess, maybe for purification purposes. Maybe we want all of the eugenol to react, so we give a lot of the give a lot of the benzyl chloride, and benzyl chloride is easy to purify out. Okay, so we could get rid of the excess of benzyl chloride. Or maybe eugenol was very time-consuming to isolate, and we want to not waste a single bit of the eugenol that we isolated. Then you would want to use compound 2 in excess to make sure that we react all compound 1 to make it into the product. So that's the stoichiometry table. I'm asking my students to do this super carefully, because this is the first time they're doing a pre-lab entry for a reactions lab. And then from here on out, organic chemistry is about reactions. It's about synthesis. So they need to follow this format and be able to do the calculations for limiting reactant and theoretical yield. Okay. And be able to give me a proper stoichiometry table with the proper ones. After that, okay, it's the procedure. So I'm not writing it out here. I want the procedure that numbered or in bulleted steps, not in paragraphs. Okay, and after that, you have observations and data. So this section you'll be filling out during the lab.